Hello, everyone. This is homework 5 solution session. Homework 5 is about the different amplifier structure design from the one we have designed in lecture 5. In lecture 5, we have designed telescopic first stage plus common source second stage two-stage amplifier. One issue we know with the telescopic structure is very limited input common range. So in this design, we have 5 stacks under 1.8 volt. So the voltage around here, they are not, we do not have much room for change. So the VDS here assigned are almost about zero point 0.3 or zero point 0.4 volt. So already the voltage here, VDS and VDS, they are very close to the VD set level. So if common level changes to high, then, well, this current source will be in danger. And if this one goes low voltage, while the voltage here is fixed, right, then the VDS of input transistor will reduce, entering it to the triode region. So almost the level here is fixed. And in our earlier design, the voltage was 0.8 volt under 1.8 volt. So the question is, well, we want to have input common level much lower than 0.8, like 0.3. So we want to modify this amplifier so that we can take input common level like this low voltage while keeping the gain and bandwidth unchanged. So we know the gain is determined by the amplifier structure here, right? The GM RO, that's the first stage gain. And the second stage gain is GM, again, RO, right? So we want to keep the gain unchanged. And the bandwidth is determined by input GM over CC. That's unity gain frequency. And second pole frequency will be determined by the output transistors, GM value, and the load capacitor. So as long as we have the same input stage here, and Miller capacitor, and of course we're gonna have the same load capacitor, right? So as long as we keep these unchanged, then we can have this one. But the only point we need to consider is this low input common level. So in order to take a much lower input common mode level, we can change the structure here, the telescopic structure, into folded cascode. So this is the folded cascode. This is the original implementation. Again, in order not to change the unity gain frequency, we keep the input stage the same. So same current source, same input transistor pair, just like the earlier design. We will keep that unchanged from the original first stage. And the output impedance, we have cascode resistance. So we will have, again, the cascode structure by having folded cascode, right, like this. Okay, so, here we should have current source, single current source. So folded cascode, right, if you recall the structure, folded cascode structure will be like this. And we have cascode here, right? And the output is going to be like this. This is the first stage, folded cascode. So the current from the input pair goes to this cascode node, and then it goes to the output. So the signal is folded. Okay, so we have this structure, and this is the current source in pink box here, and this is single transistor. The single transistor is split into two parts. One with a constant current, another for common mode feedback, just like this case. Constant current, another for common mode feedback. So in order to keep the common mode feedback characteristic the same as before, if you see the transistor size here, which takes a common mode feedback, we had here 2 micro over 400 nano. So here I designed this common mode path with the same transistor size, 2 micro over 400. And the remaining is connected to the constant current. Then what should be this current value? Well, this current value should be determined to be 220 microampere. Well, in earlier design, we had 110 microampere here. Of course, the current here is 220, right? And in steady state, in bias condition, we have 110 here and here also 110. And when signal is maximum, say like input here goes minimum, like a slew condition, even though our design in our specification, we designed the amplifier to be slew-less. But let's consider the worst case. So when the input signal splits like this, then this one will be turned off and no current will be here, right? And here we're going to have a 220 microampere current, while these guys still provides 110 and 110. So what? Because here we have current source with 110, half of the current will go to the current source, while the remaining half, 110, goes to this path. I consider it just a slew case, right? So 110 microampere goes to the output side. What if the other side? So here we don't have current. So this 110 micro current source will draw current through this path. The condition should be the same, right? I want to explain how much current we should set here and also this path as well. So when the input here is minimum and this is maximum, no current is there. The current here is going to be 220 microampere, right? Because all the bias current will go through this path. So current here is going to be 220 micro, but even that case, 110 micro should go to the output. So 220 microampere draws here, and then if we set the current source here to take hold the current, then we need to have this much current to flow here. So in the cascade structure, we're going to design this path to draw 110 microampere as well. Then the current will go through this path. And because here we don't have current, and the current source here is 220 microampere, right? So no current is there. Here is the same, 110 microampere. So because current source is there and another current source is there, the remaining current should be given from this side, which is the same case here. So we check that 110 microampere is correct. So DC or slew-wise, the current should be designed in that way. Okay, so again, the input stage is actually the same as before. This part is the same, and we need to design this current source to have 220 microampere, while this one was just 110 microampere. Well, we can design the entire current source size here to be twice of this current source, while making the common mode feedback transistor the same, 2 micro. So if you see the transistor size here, we had entirely here 12 micro. The width was 12 micro while making the L to be 400 nano. So we made a 2 micro size to be utilized for common mode feedback. So we have here 2 micro and here 10 micro. So in this case, because it was 12, we need to design this one to be 24 micro. And again, for the same common mode feedback gain, right? We need to separate this 24 micro to be 22 plus 2 micro. This one is for common mode feedback, and the 22 is for the constant bias. 22, right? It's designed like that. And the cascade here, here, because this current source is 220, right? And this is 110 and 110. So the transistor size here can be designed to be the same as this one. We use just the same size here because condition is the same. And the remaining thing is how to design this path. Well, because we need 110 microampere, while we had here 220 microampere, right? So we can just use half here and here. So if you look at the size of this source, current source, it has 40 micrometer. So anyway, the W is 40 micro here. So we can use here 20 and 20 for half the current, right? And the cascade transistor here can be just designed with the same one here, right? Because we are looking at from the output, we look at this path. So from the output, we're going to see this path and this one, but a little bit different condition, but we can have still high enough output impedance because this is current source while this is input transistor. So all the condition is pretty much the same, right? While we can provide much lower input common level because it's a PMOS differential pair and the voltage here, it can be very low, like 0.2 or 0.3. So even we can reduce the voltage here down to like a ground level. So this is pretty much about the modification, right? So two-stage telescopic structure here is modified into folded cascade. Two-stage with the first stage of telescopic is modified with the folded cascade first stage. So if you check the frequency response with actual feedback network for MDEC. And if by using CMDM, we can check the frequency response. And we find that the bandwidth is almost the same as that of the telescopic amplifier, and phase margin is also similar to it. One more thing is that different from the design here, where the high frequency pole can be generated here, and the second pole, of course, will be high frequency pole. And while this is current source, we don't have considerable pole there because signal doesn't go through that path. But in this case, we have signal path like this: output pole, which is going to be the second pole, and the non-dominant pole is made at this point, different from this point, right? So, because this is NMOS and the transistor size is smaller than this one, so we don't need to worry about this one's pole frequency, because this one will be higher than the one by the second pole. I mean the second stage or second pole, right? So we don't need to worry about this. So as a result, we got the similar performance, just like telescope first stage.